Welcome to Ask and Learn.
Okay, so this problem gives you a few sheets, 3 sheets, and then the goal is to determine, and you're given the fields in each region near the sheets, and then the goal is to determine the charge distribution. So I kind of like this problem. I feel like it's kind of a cute logic problem, but also it's obviously still a physics problem. So anyway, so this, as a kind of overview, I mean, this is going to involve the physics idea that the electric field due to infinite sheets of charge is constant and doesn't depend on where you are in space. And so, yeah, so that's like sort of fundamental to answering this problem. So I went ahead and drew the slabs, and I'm going to label them 1, 2, and 3, and then you have the field graphed here. So I'll go ahead and do that in a different color. So it was 0 on the edges, and then, oh, I made that go a bit too high. Go up here, and then it triples here to some ES value. Great. And so the goal is to get the ratio of charge from here to here. So the first thing that strikes me with this is that the field is 0 on the outside. And so you can show that that means that the net charge has to be 0 with a sort of Gauss's law argument, maybe making a Gaussian surface that encapsulates all the charges. So we know that the total has to be 0. So I'm basically, with this problem, what I'm going to do is I'm going to write out so I'm going to write out algebraic equations that like relate the charge densities based on the observations here, and then first of the graph. And then first, though, I'm going to want to determine which ones are positives and which ones are negatives. And we know if the total is 0, then there has to be some positive and negative. And then just another note, I'm just going to use sigma 1 to denote the charge on here, sigma 2, and sigma 3 to denote the charge on here. And I'll take these all to be positive in my equations. So these are all magnitudes. So first I wanted to determine which sheets are positive, which ones are negative. So I'm going to say that there's more positive because the field here is bigger than it is here. So, I mean, you kind of just generically need more pushing to the right. Yeah. So that was just a guess, and that intuition turned out to be correct. But you can always check all the negative cases. I'm not sure if there's an easier way to do this besides guess and check. So we know that there's 1 negative and then 2 positives. So let's just go case by case. So my initial intuition was that the 1 and 2 are positive, and the right is negative, just based on a physical intuition. But of course we can check. Let's check the other ones to make sure that's right. So if case 1, if this one's negative, these are positive, then in here, the field has to be less than here because here the positives cancel and here they add together. So this can't be right. And so then you have case 2, negative, positive, negative. And then for that, I think these would be, negative, excuse me. That's like not at all what I meant to say. I'm not sure why I said it in that order. So let me go back and erase that. I wanted to move the negative to the middle. Okay, great. So here's positive, negative, positive. So these fields could be, so the negatives can always be bigger if they all 3 have to add up to 0. So the fields would then be in sort of opposite. So the field here, let's see, would be some pointing this way, and then the field here would point this way. So that also doesn't work. So we know then, I'll put X's through so it's visually clear. Does not work. Does not work. However, if you put the negative on the end, that works. So I'll go ahead and draw that in a new sheet. So negative, positive, positive. So I want to take a step back. I saw this problem was rated with 1 dot, but I couldn't think of a more clever way to do this as I went along. So I'm just going to do it the algebraic way, but maybe at the end you can take a step back and consider if there's a more clever way. So onto the algebraic way. So the first equation I want to write down is that the total charge has to be 0, as I stated earlier in the video, because the field's on the outside 0. So that means sigma 1 plus sigma 2 equals sigma 3. And again, here's 1, 2, and 3. And then the other one would be the relative fields in this region and that region. So for the region between 2 and 3, you know that the field is the sum of the fields from contributions from all of the sheets. So each one is going to contribute its sigma divided by 2 epsilon naught. That's the formula that I would try to remember. I'm sure it's derived in your book. And so each one is going to contribute that. So sigma 1 plus sigma 2 plus sigma 3. And then I'll just note that they all kind of push to the right. They all three have a contribution to the right. That's why I don't have any negatives in here. Okay, wonderful. And then the final equation is for the left region. So that's ES equals 1 over 2 sigma, oh, not sigma, wrong letter. It's epsilon, not. Okay, wonderful. And then that's sigma 1 minus sigma 2 plus sigma 3. Sorry, this is so sloppy. It's harder than you would think to write with this tablet. Okay. So finally, if you kind of combine those 3 equations, this video is already getting kind of long, so I'm just going to verbally state what I do, and I'll do it in a different color. So I basically plug this in for sigma 3 here. Or sorry, I plugged it in for this. And then I got an equation for sigma 3 in terms of ES, and then I plugged that in over here. And then I plugged in, and I substituted for sigma 1 here. And then after all of that algebra, I basically got to the relationship between sigma 3 and 2, which was sigma 3 is 3 halves sigma 2. Oops. Just gonna undo. Why is this pen not undoing? Okay, I'll use the eraser because I don't want it to look bad. Oh. Yeah, this was really a lot of algebra. I really tried to do it in a more clever way. Like I drew all the vectors out and tried to see if it would just pop out, but it wasn't obvious to me. And sometimes I think it's okay, like in physics, to not just like pressure yourself to find the most clever way to do a problem, especially if the non-clever way seems sort of straightforward. If a non-clever way doesn't seem straightforward, then you probably won't find a clever way anyway.